Hello everyone. Today we want to talk about public key cryptography and some basic example of knapsack problems related to that cryptography. But first, what is cryptography? Cryptography is the science or art of sending messages such that those messages are received only by some certain people. Not everybody who eavesdrop can understand that message. So for a long time, the crypto systems that existed, they were symmetric in the sense that the same key that people used to encipher was the key that they used to decipher the code. But if you use this symmetric kind of cryptography, the problem is only the person who sends and the person who receives must have the key and not nobody else. And especially in the modern time that you want to send messages to many people through and people are far from each other, maybe the channels are not safe, or it makes it very hard for only those right people to have the code. Because of that, in 1976, Diffie and Hellman suggested a system which is called public key cryptography. In public key cryptography, there are two different keys in here, right? There is one key which is private, that only the person who wants to open to decipher the message must have it. And there is another which is public, that whoever wants to send the message can have that. And the problem was, although they set the theoretic foundations of the public key cryptography, but they didn't have good examples or mathematical examples of how to make such a thing. 2 years after that, in 1978, Merkel and Hellman suggested some special system of cryptography using knapsack ciphers. Okay. What is a knapsack cipher? And in today's lecture, I try to explain that. What are those? Because that was one of the first examples. Although nowadays probably they don't use them that much, but that was the first major example or breakthrough in terms of making those public key crypto systems. Okay. Okay. Let's say you want to send a message. You know, whenever you have a message, always you can change it to a sequence of zeros and ones. For example, you know, in modern computers, everything in your computer is in the form of a bunch of zeros and ones, right? So let's say you change your message to a bunch of zeros and one. Here, for the sake of argument, to make it simple, let's say this sequence is a very short sequence. It has 5 digits: x1, x2, x3, x4, x5. These are a bunch of zeros and ones. Some of them could be 1, some of them could be 0, and you want to send this message. Okay? Let's say, again, let's make one example. Let's say the message that you want to send is this thing: 01101, which has a meaning depending on how you did the translation to this, okay? And let's say you use the super increasing sequences to send this message. What is that? For example, consider this sequence of numbers: 2, 3, 7, 14, and 27. Why is that super increasing? Because the numbers increase very fast in such a way that whenever you add all the members of this sequence up to some point, the sum is smaller than the next element of the sequence. For example, 2 2 is smaller than 3. 2 plus 3, which is 5, is smaller than 7. 2 plus 3 plus 7 is 12, is less than 14. And 2 plus 3, 5 plus 7, 12 plus 14 is 26, which is smaller than 27. Such a thing is called a super increasing sequence. Then you can send this message 0, 1, 1, 0, 1 this way. That, for example, you have 0, you multiply 0 by this 2, and then you have 1 after that, you multiply 1 by 3, then you have another 1, you multiply 1 by 7, then you have 0 multiplied by 14, and the fifth digit was 1 that you multiply by 27, and you get this sum 0 times 2 plus 1 times 3 plus 1 times 7 plus 0 times 14 plus 1 times 27. The answer is 37. So basically the message that you want to send is this 37. Since this is a super increasing sequence, it is very easy to decipher that because of this, that you can say, okay, I have 37. 37, I subtract 27 from that, right? Definitely there should be in this sum that is 37, there should be this 27, because if not, some of the rest of these numbers is smaller than 27, and so you cannot get 37. So 27 is there, right? Then subtract now 27 from 37 and you get 10, right? So that means 14 cannot be in that sum, because if it is, you put 114, that becomes too big, right? 10, you go for the next thing, which is 7. Definitely 7 must be there, because if 7 is not there, some of the rest of this stuff cannot be equal to that. 7 is there, so you subtract another 7 from remaining, which was 10, and you get 3, so 3 should be there, and 2 is not there, so that means there should be 127, no 14, 17, 13, and no 2, which is you get back what? 1, 1, and 1 in here. That means you should have 0, 1, 1, 0, 1, which is the message that you send. So this way you can easily encipher and then decipher that message, and you are done. The problem is, of course, this is very easy. When you send that message easily, everybody can decipher that message, and so you don't want this to happen. So then what can you do? You have this sequence, but obviously you don't want to give this sequence, this information, which is a key to everybody. Question: is there any way that you change these numbers to another sequence which is not a super increasing sequence, such that if somebody receives that message, it is very hard to decipher that message? For that we need something which is called modular arithmetic. And so let me explain what modular arithmetic is. Let me turn this and get the other side of the board. Okay? Modular arithmetic. What is modular arithmetic? This is basically just like regular arithmetic of adding, subtracting, multiplying, dividing. The only difference is this, that, okay, when you add or multiply numbers, let's say in regular mathematics, you multiply 2 by 3, you get 6. You multiply 6 by 3, you get 18. Or 5 by 5, you get 25, etc., etc. Okay, but in this modular arithmetic, let's say you choose 11 as your base, okay? Everything is computed mod 11, right? So that means it is like a clock. You have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But when you get to 10, you go back to 0. Then you don't have 11 or 12 or 13. Right? You go back to this. So you have basically 11 numbers only from 0 to 10. Okay, look, one important thing, especially for these calculations, is this thing, that in here, every number from 1 to 10, every number has an inverse. That means another number that then you multiply by this number, the result is 1. For example, 1 times 1 is 1. 2 times 6 is 12, but since you reduce things mod 11, the result is 1. 3 times 4 is 12, but since you reduce things mod 11, that's also 1. 5 times 9 is 45, which is 1 mod 11. And 7 times 8, which is 56, that minus 11, 11, 11, 11, you subtract 55 and you get 1. So, as you see, every number from 1 to 10 in here has a multiplicative inverse. That means a number that when you multiply by that, the result is what? The result is 1. Okay, now let's go back to the sequence that we had, which was a super increasing sequence. And that was let's say that was A1 to AN. Of course, here in these examples, I make all the things very short for practical reasons. Definitely, you should have much longer sequences. So, okay, and choose a module M, which is bigger than 2 times the biggest of the elements of that sequence. Let's say you choose that M, and let's say you choose a number which greatest common divisor of that number W with this M is 1. That means W and M are relatively prime to each other. W. Okay? Now, for that sequence that you have, which is a super increasing sequence, multiply this W, which was the number which is relatively prime to M. Multiply this W by all of these elements. So, instead of this sequence, you get W times A1, W times A2, W times AN, but you do your computations in that mod M. So, WA1, let's say is B1. WA2, let's say is B2, to WAN is BN, okay? So, now, you get a new sequence, B1, B2 to BN, which is not super increasing sequence anymore, right? These numbers just randomly could be anywhere, and it is not super increasing. Now, let's say if you publish this as the key, and somebody wants to make, let's say, has a message, wants to send that bunch of xi, which are zeros and ones, right? Can do this. Can take these zeros and ones and multiply by these and get this summation. This means B1x1. This summation means sum of B1x1 and B2x2 and B3x3 and B4x4 to Bnxn, right? Instead of A1 to AN, which was super increasing, now is using this sequence, which is not super increasing. Okay, the problem is, okay, let's say they get a number, but when they have that number, how do you want to decode that and get the original message? The point is, only you who know this must be able to decode this one and nobody else. Okay? The key is now, let's say you remember that W, and that W must have some multiplicative inverse. We call it W bar, that when you multiply W by W bar, the result is 1. If you multiply this W bar by this becomes by both sides of this is W bar S, and if you multiply W bar by this W bar is multiplied by each one of these BI's. But you remember, W times AI was BI, so W bar times BI, since W bar is the inverse of W, must be AI, which is this thing. So this becomes summation of AI xi's, which is now AI, you remember that was a super increasing sequence. So it is very easy now to this number to break it and recover the original message that you had. Okay? Let me quickly do one example on that, because that was the general idea. Look, let's say you have this sequence 3, 5, 9, 20, 44. This is a super increasing sequence because 3 plus 5 is 8, this is less than 9, 3 plus 5 plus 9 is less than 20, etc. Okay? This is the sequence this is the key that you have to keep it private, right? But now, let's say you work things mod 89, right? Let's say you choose mod 89, and let's say you choose a number, let's say 67, right? Look, 89 is bigger than 2 times this, right? As we mentioned in here. Okay, and now choose a number, let's say 67, and multiply 67 by all of these mod 89. Let's say 67 times 3 and reduce it mod 89. You get 23, and for 5 you get 68, and you get a sequence of 5 numbers. This is super increasing, but this one obviously is not super increasing, as you can see. Okay? So, for example, let's say in here somebody has a message from x1 to x5 and takes these things and multiplies by this, which is now the public key, right? x1 times 23 and 68 times x2 and 69 times x3, and creates a number, let's say, depending on the message. Let's say when these are multiplied by these numbers, the answer is 84. Okay, now the question is when you get 84, how can you figure out what is the original message? Look, 67, the inverse of 67 mod 89 is 4. The only thing you need to do is multiply this number by 4 and all these also by 4. When you multiply 4 by each one of these, since 4 is inverse of 67, you get back 3, 5, 9, 20, and 44, right? So then you multiply 4 by 67, you multiply 84 by 4 and you get 69, and the only thing you need to do is take this 69 and using this super increasing thing, figure out, okay, 69 is equal to what? 69, look, 44 must be there. Also 20 must be there, which is 64, and 5 must be there, which makes it 69, and that's it. That means there is no 0, there is no 3, there is no 5, there is one 5, there is no 9, there is a 20, and there is a 44. So you get the message that the message was 0 here, and 1 in here, and 0 for 9, and 1 for 20, and 1 for 49, and that was the message. And that's basically the idea. Thank you so much for listening to me. I hope that you got some general idea that how these knapsack problems that we use to create crypto systems, public key crypto systems work. Thank you so much, and you have a great day.